JQI seminar, so welcome to people coming for that. And Daniel's going to tell us about error suppression for Hamiltonian quantum computation.
Okay, good morning. Thank you, organizers, for the invitation. It's really QEC. Some of you here may remember QEC 1, which took place at USC back in 2007. It was a smaller meeting, and it's great to see so much interest in this field. It's sustained itself. I have to say that the organizers of this meeting did not ask the organizers of the first meeting, which included Todd Brunn and myself. By the way, Todd couldn't make it. He sends his regrets, for permission to take on the franchise, but that's okay. It's free. Now, Jake mentioned that this is also the JQI seminar, and he caught me out in the hall and he said, can you say some general things about the future of quantum error correction? And I did not plan to do that in this talk. This will actually be a fairly technical talk. So apologies to those who will find this more technical. But Jake, if there is time at the end of the talk, or if you want to give me some extra time, I did actually pull out a few more slides that have a more general flavor than this talk. So we can go there if you'd like. Okay, so without further ado, I'd like to talk about error suppression for Hamiltonian quantum computation. I'll define that in a second. And this is work that draws primarily on these three papers with Iman Marvian and Milad Marvian, who are related, in case you're wondering. And they're both here today. So let me define what I mean by Hamiltonian quantum computation, first of all. So first of all, I think all quantum computation is Hamiltonian. That's almost that's a trivial statement. The point is that everything is generated from Hamiltonians, and of course there's no such thing as an instantaneous gate or an instantaneous measurement. Everything is always continuous, and that's fundamentally why Hamiltonian quantum computation is interesting. But more specifically, what I have in mind are things like adiabatic quantum computation and quantum annealing, holonomic quantum computation, certain forms of topological quantum computation, some forms of quantum simulation, and self-correcting quantum memories. These are all examples where the notion of Hamiltonian quantum computation is relevant and useful. So the goal of what I'd like to talk about today is how we can protect Hamiltonian quantum computation against decoherence. And I'd like to do that without invoking active error correction. So we're removing that ability from the scenario today in this talk. In other words, no measurements, no feedback, just passive error protection or error suppression. And you might wonder why we'd want to handicap ourselves in this way. And the answer is that, this certainly sets certain lower bounds for what we can do. So we might ask, what are the fundamental limits of this kind of a passive approach? Obviously, it has some theoretical and experimental simplifications if we take out the measurement and feedback step. And it gives us a lower bound on how well we can do once we introduce active error correction on top. So the basic question I'd like to answer in this talk is how much error suppression we can obtain using the passive approach. So a good starting point to talk about this is the work by Jordan, Farhi, and Shor from more than a decade ago now on protecting adiabatic quantum computation using energy penalties. So let me briefly remind you how that scheme works. So again, this is the setting is adiabatic quantum computing. We're not going to do any kind of measurements or feedback. So consider a set of Pauli errors, call them sigma, and let's find an error detecting stabilizer subspace code, call it C. So the first step, after we find the code, is to encode the Hamiltonian. This is the computational Hamiltonian that performs the adiabatic quantum computation. We encode it. The ground state becomes the encoded ground state. And then the key step is to add an energy penalty term. So HP is the energy penalty Hamiltonian, EP is the strength of this term, and the sum here is over all the stabilizers of this error detecting code. Let's say there are G of them. So what happens then is that, well, the code states are by definition the simultaneous +1 eigenstates of all the stabilizer generators. And if you check the action of the penalty Hamiltonian on the code states, you see that they're degenerate and they have an energy of negative the number of stabilizers times the energy penalty under this Hamiltonian. And they span its ground subspace. But what happens when we have an error? So because the code is error detecting, each Pauli error that's detected by the code anti-commutes with some number A greater than 1 of generators, and it commutes with the rest. So if phi bar is a code state, then the erred state, sigma phi bar, is still an eigenstate of the penalty Hamiltonian, but it has a higher energy than the code state. So it pays an energy penalty of twice EP, twice this, for each of the A generators that the error pays for each of the generators that it anti-commutes with. So code states are ground states, erred states are excited states, and this suggests that we should perform computation in the ground subspace of the penalty Hamiltonian, which is spanned by the code states. And the detected errors are now suppressed because they get an energy penalty. So that's the scheme that JFS, Jordan Farley Shore, came up with. And we may ask how useful this is. Well, they partly answered that question in their paper. What they showed was that if you consider the initial change in the system density matrix, then it is given by a Hermitian term. This is just the Hamiltonian that performs the adiabatic quantum computation. I guess this should be HS bar. It's the encoded Hamiltonian now. And then there is a non-Hermitian term, but that non-Hermitian term is suppressed exponentially. So for fixed temperature or inverse temperature beta, the suppression is exponential in the energy penalty, EP. So that's essentially, that's the key result. There is an energy suppression. There's a suppression, an exponential suppression in the strength of the energy penalty. And in order to prove this, what they assumed were some fairly specific assumptions, but as you'll see, easily generalizable. They assumed a Markovian model that describes a spin system that's weakly coupled to a large photon bath. They specifically analyze codes that detect 1 and 2 local noise. And they also assume that the ground state is non-degenerate and pure. So the first question I'd like to answer is whether this work can be generalized. In particular, instead of the specific model, can we deal with arbitrary adiabatic Markovian dynamics? Instead of these specific codes, can we deal with arbitrary stabilizer subspace codes? And can we even relax the assumption of a pure ground state and deal with arbitrary, degenerate, mixed ground states? And the answer is yes, and it's the work is in this paper with Milad Marvian that was published this year. So very briefly, let me explain the result that we found in this paper. So we start from a general adiabatic Markovian master equation, not even necessarily in Lindblad form, in which we derive from the system bath interaction with system operators A sub alpha that are assumed to be K local with K constant. We assume a bath in thermal equilibrium at some inverse temperature and a spectral density high frequency cutoff. And for this particular set of errors, we assume that there exists an error detecting stabilizer subspace code, C, and that's the error detection condition right there for all the errors that appear in the system bath Hamiltonian. So now we follow the JFS prescription. We write down the total Hamiltonian as the encoded adiabatic Hamiltonian plus an energy penalty term, which is just the sum of the stabilizers of this code. And let's say we spectrally decompose it. So the pi L are the projectors onto the eigenspaces. And let's say that we prepare an initial state in the ground subspace of this Hamiltonian, and this need not be a pure state. This could be an arbitrary mixed or degenerate state. So the result that we then find, which generalizes the JFS scheme, as you see, the assumptions here are beyond what was considered in the original paper. The result is the following. So we explicitly consider the initial excitation rate. So this, you can identify this quantity as the rate of transitions outside of the ground subspace. Pi 0 projects the state into the ground subspace. And this initial excitation rate is upper bounded rigorously by a Boltzmann factor that's exponential in the inverse temperature, the energy penalty, and the constant gap of the penalty Hamiltonian. So this is the key quantity. And then there's also a polynomial in the energy penalty, and importantly, a polynomial in the number of qubits, n. Okay, and the source of these terms is explained here. It's actually kind of surprising that there's a polynomial here. Naively, you might expect that there should be exponentially many, that there should be an exponential in n here because there are exponentially many excited states. But it turns out that it's only a polynomial because of the error detection condition. So if you look at this expression, you see that the energy penalty, in order to overcome this polynomial in n, the energy penalty only needs to grow as log n for any fixed inverse temperature beta. And this is a conclusion that was already there in the original JFS paper, but they actually didn't prove it. And so in our work, we now establish this rigorously. So the bottom line is that for these Markovian models, using error detecting codes, stabilizer subspace codes, we can rigorously show for appropriate baths that the initial excitation rate is indeed exponentially suppressed in the strength of the energy penalty. So that's good news for the Markovian scenario. But there's another consideration that we must remember, and this is locality. And much of what I want to say next has to do with the question of locality. So first of all, if we have a code that is supposed to detect all k local errors, well then the logical operators have got to be at least k plus 1 local, because otherwise they will themselves look like errors, and that's not good. And so in the JFS case, they wanted to protect against 1 local errors, and they found a code that has 2 local logical operators, which is good, because then these logical operators aren't themselves suppressed by the code. But the stabilizer generators, in the case of the code that they found, are 4 local. And these are terms in the Hamiltonian, right? The penalty Hamiltonian is constructed as a sum over stabilizer generators. And so now we have a penalty Hamiltonian that is 4 local. And that's less pleasant, certainly hard to implement experimentally. So the question is whether fully 2 local error suppression is possible. Right? That would be a nice scenario, because experimentally it's much easier to implement all 2 local operations, not operations, interactions, 2 local interactions, as opposed to 4 local or even 3 local. And the answer to this question is that it really depends. And the first scenario I want to discuss is essentially a no-go theorem against all 2 local error suppression. And the case I want to focus on is what happens when we have commuting interactions. So this happens in a variety of interesting cases. Let's say we want to store quantum information in the degenerate ground subspace of some code C that is protected by a constant gap delta. And this is what we want to do in self-correcting quantum memory and holonomic quantum computation, topological quantum computation. So Hamiltonians that are formed as sums of commuting terms are natural for this setting because they have gapped ground states, as was shown in this paper. And that, of course, includes the example of the JFS scheme that I talked about. Now, you might ask, can we do fully 2 local error suppression in this setting of storing quantum information in a degenerate ground subspace with a constant gap? And the answer is no, there's a no-go theorem that appeared in this paper with Iman Marvian. So the theorem says this, that even if all you want to do is store information, not compute, so let's set the system Hamiltonian to 0 and consider just a penalty Hamiltonian. So even if we just want to store information, even if we assume that the gap is infinite, and we allow q dits with arbitrary dimension d, then commuting two local terms fail. And they fail because they cannot suppress arbitrary single particle errors. There will always be a single particle error or a single q-dit error that is going to create an excitation. So we call this in this paper, too local is too local. So here's a brief sketch of the argument with a bit of detail. So consider a gapped Hamiltonian, H naught, which is in whose ground state or ground subspace we want to store information. And let P sub C be the projector onto this degenerate ground subspace. So essentially what we showed in this paper was that the following. Project and, or first evolve under the Hamiltonian H naught, plus a perturbation V, and then project. So compare this operator to this operator, and the statement is that the difference between them goes to 0, like 1 over the gap. So when the gap goes to infinity, the difference between them goes to 0. So that means that effectively the Hamiltonian that governs the evolution, it can be thought of as not H0 plus V, but rather the projected perturbation. Call it V prime. So V prime is essentially the Hamiltonian that governs the evolution under the scenario of an infinite gap. And you might recognize this expression from first order perturbation theory, so it's not too surprising. Now, if this is the effective evolution, that's okay if the quantum error detection condition is satisfied, because the quantum error detection condition assumes that this is proportional to the ground state projection. So in that case, we're just staying in the ground subspace of this Hamiltonian H naught. But the no-go theorem says that that can't happen for two local commuting Hamiltonians. The effective Hamiltonian V prime can never be proportional to the ground state projection for commuting two-body Hamiltonians. So that means that the quantum error detection condition is always violated, and therefore such two local commuting Hamiltonians are effectively useless for error suppression. We can make that statement more explicit. We can compute the T2 dephasing time, where here T2 is defined as the timescale for the decay of off-diagonal elements of the density matrix in the eigenbasis of V prime. And what we find is that this T2 is always upper bounded. You can't make it infinite by a quantity that goes like the inverse of the perturbation norm. Now the proof of this result is involved technically, but essentially the reason that this happens is that when you have two local commuting Hamiltonians, it turns out that they have no more entanglement than just a single pair of q-dits. So there's just not enough entanglement in the ground subspace in order to spread out the errors. That's the intuition. Okay, so then what can we do to get fully two local error suppression? We can't use commuting Hamiltonians, two local commuting Hamiltonians. And there are two alternatives that I'd like to discuss. There might be more. One is dynamical decoupling, and the other one is codes that are outside of this framework of two local commuting Hamiltonians. In other words, non-commuting. So let me first quickly talk about dynamical decoupling. This is rather old work, but it fits in this context. So in order to use dynamical decoupling, what we should do is make the computation, let's say the adiabatic quantum computation, commute with the decoupling pulses so that they don't interfere. And to achieve this, the idea is to, like in JFS, encode the system Hamiltonian using the code's logical operators, and apply the code stabilizer generators as dynamical decoupling pulses. And this is key because these are now unitary operators. And so if they're k-local, that means they're k-local as a gate, not k-local as a Hamiltonian. Now, what we need in order to make this work with the two local case is we need a distance to code that detects one local errors that has at most two local logical operators. And it turns out there is such a code that has at most two local logical operators. It's an n-2 to stabilize a code, and these are the code states. And here's an example for n equals 4 that gives you two logical qubits. Right? Here are the four states. The stabilizer generators are the global x and the global z, and these are going to be applied as dynamical decoupling pulses. So again, unlike the error suppression setting where this would be an n-body interaction, which is not good, now this is just a gate acting on n qubits, and that's okay. So here's a cartoon to show what the scheme looks like for this code that I just mentioned. The logical x on a logical qubit j is sigma x between qubit 1 and j plus 1. Z is this. These are both two local interactions. The xx is also two local. It's a sigma x between physical qubits I plus 1, j plus 1, and likewise zz. So all the logical operators are two local. The dynamical decoupling pulses, as I mentioned, they're just global either x or z pulses. These are the two stabilizers of this code. And we can apply these simultaneously with the logical operators because they commute with the logical operators. So this allows us to do fully two local error suppression, not using a Hamiltonian gap, but rather using dynamical decoupling. How well does this work? Very briefly, here's a figure from this paper here with Greg Carroz. We looked at this numerically for the adiabatic Grover algorithm. What you're looking here at is the trace norm distance between the protected, dynamical decoupling protected state, the evolving state, and the eventual ground state as a function of time, total evolution time in units of 1 over the gap. And if you can discern the black curve, it's way at the bottom here. This is the ideal case when there's no noise. This is for a Gaussian bath for two encoded qubits. And the upper curve here, the purple one, is when we don't do any dynamical decoupling. And everything in between are dynamical decoupling pulse sequences at various levels of concatenation. So concatenated dynamical decoupling is an idea where you recursively nest the pulse sequences into each other in order to create pulse sequences that have increasingly higher order decoupling power. And if you do that, when the total evolution time is fixed, you make the pulse intervals smaller and smaller. Making the pulse intervals smaller is like increasing the total energy available to the system, and that is similar to the idea of increasing the energy penalty. So you can think of increasing concatenation as increasing the energy penalty. And indeed, as you increase concatenation, the performance gets better and better until it becomes indiscernible from the ideal evolution for this Grover example. And here's another example, two sat on a ring, and it's the same story. As you increase concatenation level, the evolution becomes indistinguishable from the ideal. So this idea works. In fact, there is a formal equivalence between the dynamical decoupling approach and the energy penalty approach, as was shown by Kevin Young and Mohan Sarwan and Robin Bloom-Cahoot. Briefly, what they observed is that if you do dynamical decoupling with stabilizer pulses, so here's the total Hamiltonian, and here's the system-bath interaction, you sandwich it between dynamical decoupling stabilizer generators, and you obtain this expression for the effective Hamiltonian. So you see that the system-bath interaction is now modulated. And if you consider the energy gap protection scheme with a penalty Hamiltonian that's a sum of stabilizer generators, well, it's actually not surprising that the two are very similar, because here we're applying a product of stabilizers And here, the Hamiltonian is the sum of stabilizers. So if you exponentiate it, you get a product of stabilizers. And indeed, if you consider the time evolution, what you find is that the effective Hamiltonian looks very similar to what you get with dynamical decoupling. The difference is just that here, because there's a switching function, it goes like plus minus 1, whereas here it's just a general vector rotating. But in both cases, whether you do dynamical decoupling or energy gap protection, what happens is you take the system Bath Hamiltonian and you modulate it fast, and that averages it out, and that's why both schemes seem to work. Okay, so that's all I want to say about dynamical decoupling. Now, let me switch gears and go to the other way out of the no-go theorem for two local interactions. So after Iman Marvian and I published our paper, we kind of forgot about it and figured that maybe somebody else would come up with a way to evade the no-go theorem. And indeed, it didn't take very long. Jiang and Riefel found a way to overcome the no-go theorem by relaxing the assumption of commuting to local. They went to the non-commuting setting. And they showed that there were examples they found where non-commuting, purely to local Hamiltonians, in particular using certain generalized Bacon shortcodes, did the job of providing error suppression. So in a recent paper with Milad Marvian, we generalized this to arbitrary subsystem codes and also provided rigorous performance bounds. So that's the last thing I want to talk about. So here's a theorem that we proved in this paper on error suppression with general subsystem codes. So I'm sure most people here are familiar with the idea of subsystem codes, but quick recap. Suppose you decompose the system Hilbert space into a direct sum of some code space C and an orthogonal space C perp. And let's say there's a tensor product structure on C. And let's call this component B, this subsystem, the information subsystem. And A is going to be the gauge subsystem. So in B is where we store our information. So here is the system Bath interaction Hamiltonian with some system operators S sub j, Bath operators B sub j. Consider the S sub j the errors. And we formulated an error detection condition for these errors, which looks a lot like a Knilla-Flam type error detection condition. And it says that for every error, there should be some operator G such that the projected error has trivial action identity on the information subsystem. That's the error detection condition for subsystem codes. So then we choose a code that satisfies this condition. We choose a penalty that commutes with the encoded system Hamiltonian. So here's the encoded system Hamiltonian. Here's the penalty. Here's the Bath Hamiltonian. Let's add them up and call that H0 prime. And let's also eigendecompose the penalty Hamiltonian. And then the theorem says this. This is similar to what we saw earlier with the no-go theorem in structure. The theorem says that if you consider the total evolution, which is this is kind of a decoupled evolution from the perspective of the encoded information. But if you add the system Bath interaction to it, you get the total unitary U sub t. Project that to the code subspace. That goes to U prime projected on the code subspace, where U prime is the decoupled evolution plus some additional term that involves these projectors that appear here in the decomposition of the penalty Hamiltonian. But importantly, the identity action on the information subsystem. So basically, this extra term doesn't do any damage because it acts like identity on the information subsystem. And this goes to 0 like 1 over the strength of the energy penalty. So the theorem says that provided that you pick a code satisfying the error detection condition, a subsystem code now, and you choose the penalty appropriately so that it commutes with the encoded system Hamiltonian, then you can guarantee that in the limit of a large penalty, the actual evolution is just like the ideal evolution where everything is decoupled, provided you project onto the code subspace. So that's the generalization. And this does not invoke the notion of locality, of too local, or those are things that now have to be checked on a case-by-case basis, whether you can now use this more general structure in order to evade the no-go theorem. And it turns out, as was already observed by Zhang and Riefel, that the answer is yes. And so the specific setting for that is stabilize the subsystem codes, which were formulated in this paper by David Poulin. So quick reminder, stabilizer subsystem codes look like this. There are stabilizers, there are gauge operators, and there are logical operators. These three sets commute. We form the gauge group, which is, we take the stabilizers and the gauge operators, and this is now non-abelian because the gauge operator set is non-abelian. And now what we do in order to satisfy the conditions of the theorem is first we encode the system Hamiltonian over the set of logical operators. We replace the penalty Hamiltonian, which used to be a sum over stabilizer generators, by a new penalty Hamiltonian, which is a sum over gauge group generators. Okay, so this is the key modification that we have to make. The penalty Hamiltonian is not a sum over stabilizers, but rather a sum over gauge group generators, which means that there are non-commuting terms here. But because of the structure of stabilizer subsystem codes, we know that the penalty Hamiltonian commutes with the encoded system Hamiltonian, so that condition in the theorem that they have to commute, that condition is automatically satisfied. So now I can give you examples of fully two-local error suppression with non-commuting Hamiltonians. Okay, and so the first example is the one that Zhang and Riefel came up with. It uses a 412 code. Here is the stabilizers. The stabilizers are just XXX and ZZZ. The gauge set, the logical set, and we form the gauge group. We manipulate a little bit, and we can show that it's equivalent to just a set of two local interactions. And it's easy to check that this set of two local interactions on 4 qubits detects all one local errors. So it's fully protected against one local errors. And so here's what it looks like. The penalty Hamiltonian is a sum over these 4 operators. So if blue is XX and red is ZZ, that's what the penalty Hamiltonian looks like. And the encoded system Hamiltonian, well, these are the logical operators X1, X3, Z1, Z2. So that's what that looks like. Okay, so we have a fully protected logical qubit using just 2 local interactions against arbitrary 1 local errors. And the key is that this is a set of non-commuting operators. So that evades the no-go theorem. Now the caveat here is that this is not good enough to do universal quantum computation with 2 local operations, because you can check that the encoded 2-qubit operations are 4 local again. So it just works for protecting single qubits, but not to create interactions with 2 local interactions. Here's another example. This is protecting the adiabatic swap gate, which is a key component in the proposal by Dave Bacon and Steve Flamia from a few years ago on adiabatic gate teleportation. So in their work, they showed that if you consider this Hamiltonian, with S, think of S as time going from 0 to 1, so you slowly turn off this term and slowly turn on the other term. They show that any state that is initially prepared on qubit 1 transfers on to qubit 3 if you do this. I may have gotten the S wrong. Maybe S goes from 1 to 0. So what we would like to do now is to take this adiabatic swap gate and protect it against 1 local errors using just 2 local interactions. And this we can do. We need an 832 code. So here are the 8 qubits. And it turns out that the penalty Hamiltonian in this case is just the sum of XX and ZZ terms, as indicated here. And the encoded system Hamiltonian is even simpler, it's a sum of just 4 xx and zz terms. And that's a bit non-trivial to show. You have to kind of play around with the multiplying stabilizer operators until you, and gauge operators until you reduce everything to a two-local form. So we can protect the adiabatic swap gauge using just two local interactions. And as a final example, consider the open chain transverse field Ising model. So a transverse field here, ZZ terms, and so this is ubiquitous in quantum annealing. And if we'd like to protect this against one local errors using only two local interactions, again, we can do that. So here we need, well, there's a general N here, so we need a more general codes, and using a construction by Bravi for generalized Bacon-Shor codes that we borrowed, we found a 2n plus 2 n2 code which does the job. It's fully two local. And so here you see the encoded system Hamiltonian. So we started with a chain of n, and so now we have 2n plus 1 plus another one, so 2n plus 2. And it turns out that, for example, logical x is xx here, and logical zz is zz here, etc. And likewise, the penalty Hamiltonian is simple to construct using only purely two local interactions. Unfortunately, there is a caveat with this example, which is that unlike the previous two examples where the gap was constant, here the gap actually decreases like 1 over n plus 1. And so this is not so good because it means that you also have to increase the energy penalty like n in order for the protection to remain in place. But still, apart from that, we can do this, protect using only two local interactions. So you signaled 5 minutes, which means 3 minutes until, including questions or without? Okay, great. Okay, perfect. So what I'll do then is I thought I would give you a sketch of the proof of the theorem, but I'm going to skip that. And you can ask me about it if you're interested. It's a nice little proof, which is inspired by work by Bukatz, Farhi, and Zhu. Anyway, let's just go to the end. So let me summarize and pose some open questions. So the first message is that big gaps alone, contrary to what you might think if you have some kind of a Boltzmann argument in mind, right? E to the minus delta over kt, that goes to 0 as the gap gets large. That's not enough. Because you also have to think carefully about the type of interactions involved. And in particular, the no-go theorem shows that even if you take the gap to infinity, commuting two local interactions don't offer protection against arbitrary one local errors. However, we can suppress one local errors if we go from two local interactions to four local interactions. And that was already shown by Jordan, Farhi, and Shor. So it's interesting that they also ruled out three local interactions, but only in the context of stabilizer subspace codes with q bits. So as far as I know, the problem of protecting against one local errors with three local commuting interactions outside of the stabilizer subspace code framework or allowing q dits, that's still open. So that maybe is low-hanging fruit for someone to pick. Now, we can suppress one local errors with two local non-commuting interactions, but for that, we have to go again outside of the stabilizer subspace framework. We have to go to subsystem codes or even more general subsystem codes. A big open question is how to do universal adiabatic quantum computation using energy gap protection using fully two local interactions. The Zhang refill example is nice, but it still involves four local interactions if you want to do logical 2-qubit interactions. However, we do know how to do this, as I discussed, using dynamical decoupling. And there's an equivalence between the two, and that equivalence hasn't been sufficiently explored or exploited, in my opinion. And finally, the perspective that I've taken here is that any coupling to the bath is always bad. But we know that's not the case, because relaxation in adiabatic quantum computation or quantum annealing is good. It takes us back into the ground state. So relaxation should be encouraged. The problem is excitations. You might say there's no relaxation without excitation, but still, can we find codes that suppress excitations but enhance relaxation? Is there a way to do that? I think that's an interesting open question as well. So with that, I'll thank you for your attention.